Hello? Is it clear? Okay. Not too loud, not too weak. Okay, perfect. And finally, this one starts working. I don't need to use this one. Okay. Let's get started. So first, we just want to remind everyone, our quiz one has been released. It should be available after this class until I think midnight of Friday. 15 minutes, 3 single choice, or perhaps multi choice, is up to you, like problems. I won't take you too much time, but try not to miss it, because we won't have room for makeup, because the exam answer will automatically pop up after the deadline. That means like if you open it after that, it will just automatically show all the answers. It won't be fair to ask you to take that. Okay, and again, if you just happen to miss that, don't panic, because we'll drop the 2 lowest grades among all the possible quizzes. Just try not to miss too many, like more than 2 that will affect your grade. Otherwise, it won't affect your grade.
Quiz is based off last week's stuff, right?
Yes, yes. Labs also covers something we haven't taught. We're going to talk today. Good question. Any other questions? Okay. Another thing is about is that our first homework has been released. Again, I think it's just 3 problems. And again, if you have some time, please start doing it early. Don't rush at last hours. And also, we have office hour every weekday, and feel free to ask for help. And we request you to write down directly. You can print out the PDF and write with your pencil and scan, or you can use iPad, download PDF, and you know, like what I did here, using Apple Pencil, whatever, to write it. Just make sure to write clearly. Otherwise, the TA might, unnecessarily deduct your points, and it will take you some time to argue with them. It's not very efficient. Okay. Any question regarding our homework assignments and quiz schedule? Okay, great. So let us continue. So in the last lecture, we started talking about how we're gonna use a formal way to describe uncertainty, right? So we talk about what's the definition of events, sample space, and probability functions, right? But all those are based upon the so-called sets. Right? So what is a set? What's a set? Exactly, right? It's just literally what I said in the last lecture, yeah. It's just a collection of objects which are non-repeatable, which are unique. That's it. And you can put numbers in your set. You can put apples, oranges, or whatever objects of interest into your set. And your set can be finite, it could be infinite, could be infinite, uncountable, whatever. It's just a collection of objects, right? So then if we consider investigating some kind of random experiments of interest, right? Here, experiment does not necessarily mean that you're doing some scientific experiment. You can do whatever you want to investigate whatever things you feel there is some randomness. You can call it random experiment, like you do gambling, right? You do gambling, or you roll a die, you look at dice points, right? Those can be called random experiments as well, right? So then we define the concept called sample space. So what is sample space? Exactly, right? So sample space is a particular type of set. This set contains all possible outcomes of a random experiment you're interested in, right? For example, if what you're interested in, just to roll a die, right? So then your outcome your sample space will be just 1, 2, 3 until 6, right? Because you only have like 6 possible outcomes, right? Represent the points. And suppose your random experiment is just a toss a coin, then your sample space just heads up or tails up, right? So that's your sample space, right? And then what are the events? How do we represent a event? Yes, exactly, right? So that's why sets are so fundamental, because we represent any random event by a set. And this set is a subset of the whole sample space. For example, I mean, using that rolling die experiment as example, we know that our sample space is just 1, 2, 3, 4, 5, 6, right? And if I can come out an event, like my event A would be, I got point less than or equal to 3. How can we mathematically represent this event? Any thought? Mathematically, how are we going to represent this event, right? Of course, when you use human language, we'll just say, okay, I got a point less than or equal to 3, right? Or no more, or no bigger than 3, right? But how do we represent A? You got. Yeah, of course, that's one way of saying that, right? But if we write it in most, I mean, straightforward way, would be, yeah, just 1, 2, 3. Remember, so this is the human language. This is the math language, right? So just represent it as 1, 2, 3. Right? Remember, an event is just a subset of the sample space, right? And of course, I can define another event would be I got my point. I got an even point, right? So how can we represent B? Yes, exactly, right? That's how we're going to represent it, right? So, and once we have defined those events, which are essentially just the sets, right? We can operate on those sets and to generate new sets. These new sets will represent new events, right? Like, what kind of set operations have we talked about? Yeah, the most important two operations, right? Union and section, right? So union means you just merge all the elements between the sets together, right? Of course, you're gonna deduplicate, right? If we take a look at this two sets, we have just written, right? What is A union B? Yeah, A union B, what's that? Yes, A and B, and what's the corresponding set? That is fine. Yes, you can see that. You just merge the elements in this two sets into a new set, right? Of course, you're gonna remove the redundant ones, right? So it'll be just 1, 2, 3, 4, 6, right? That's called union, right? So the other is the intersection, right? What's the intersection? Yes, just 2. You just pick up the elements shared by both sets. And for this case, A is 1, 2, 3, B is 2, 4, 6. There's only one element shared, right? So the intersection will be just and singleton set, right, which contains 2, right? Okay, good. But there's in addition to this, like most two common and commonly used the important operations, union, intersection, we also have a complement, right? So what is complement? Exactly, right? So complement is just like, okay, I have a whole set, which we call sample space, right? And this is your set A. You just exclude elements of A from your sample space. Then the remaining is the complement of A. So in our case, our whole set or sample space is 1, 2, 3, 4, 5, 6, right? Your A is 1, 2, 3, then the complement will be what? 4, 5, 6, right? Yeah. Okay, that's another operation. And the last operation, which might not be that intuitive, is called set difference, right? Which written as A subtracted by B, right? What's the set difference? Can anyone recall? Yeah. 1, 3, 4, 6. Is it a hint? The set difference won't like merge the terms, the elements that not in the original set. Yeah. Yeah, exactly. You got exactly, right? Exactly. That's the definition, right? So the difference means that, okay, I'm gonna remove the elements of mine, which are also inside the other guy. So this is called difference, right? So if you look at A here and B here, you know that there is only one element, 2 here, which is also inside B. So I'm gonna remove it as my result, right? So it will be 1, 3, right? And then what is B minus A? Why is the empty set? Okay, this is a key point we want to emphasize. The difference is not like, okay, A must be bigger than B, in terms of size, or B must be bigger than A in terms of size. The difference here, the minus sign here really means that, okay, I'm gonna remove those common elements across the two sets. Yeah, exactly, right? So if we look at B, I want to look at which elements in B are also in A, which is only 2, right? So I'm gonna remove it. So the remaining will be our result, which are 4 and 6. Right? So this is a little bit not that aligned with the numerical or arithmetic definition of minus sign. So it's a little bit, please be a little bit attention on this. Okay, so that's basically contains all the set operations we need to know: union, intersection, complement, and the last one is set difference. Okay, so what is the meaning in terms of events? Right? As we mentioned, event is defined as some kind of set, right? When we do those kind of operations between different events, they're going to generate new events. There will be some meanings along these new events. So let's look at A intersection with B. So A is an event, B is event. So A intersection with B represent an event that both even A and B happens. Right? So like even A could be there will be snow tomorrow. Even B will be I get up late in the morning, right? So A intersection with B means that I get up late in the morning tomorrow, and also there is a snow. Right? So these two events must both happen. That means like intersection, right? So then what does A union with B mean? Right? It means a new event that A happens or B happens. It also includes the case that A and B both. So you can imagine this represents a larger possibilities, right? Going back to the examples, right? So A is there's a snow tomorrow, right? B is I get up late, right? So A union with B means that I get up late or there's a snow, right? It could be like I get up late, but there's no snow. It is included in this A union B. It could be there's a snow, but I get up early. It also indicates one possibility for A union with B, right? And also could be I get up late as well as there's a snow. So you can see A union B is covers like more possibilities or activities than A intersection with B. That's why to give a more intuitive representation of this, right, we suggest using the Venn diagram, right? So you can use a circle to represent A, and you can use another circle represent B, right? So A union B just means all the areas covers by A and B, but A intersection with B is just the overlapping part, right? So from that, we can have an intuition why A union B conceptually is bigger than A intersection with B. Does it make sense? And A complement. A complement is pretty straightforward. So A complement represents the even A does not happen. A represents the even A happens, right? The complement A, it just means the even A does not happen. It's like A is like, okay, tomorrow there's a snow tomorrow morning, and then A complement means there's not a snow tomorrow morning. Okay, so the last one is about the set difference, right? So we say there are two events A and B. Then if we construct a third event, A minus B, it just represents even A happens, but B does not. Right? Like even A could be there's snow tomorrow, B I got up late. Right? And A minus B means there is snow tomorrow morning, but I get up early. Right? I do not get up late. We still stick to get up early and get to the school, right? I don't miss my class. I don't miss my duty, whatever, right? Okay. Any questions so far regarding? Oh, okay. You mean in terms of the notation? Yeah, that's a good question. So yes, And in some, I believe in most textbooks, they will just use this one, A minus B, to represent the set difference. But you will see some literature, they use A slash B. Well, maybe this one is even more intuitive because it sounds directly related to, okay, I'm gonna excluding part of A, which is inside B, right? So, but whatever, right? If you say A slash B, it just means A minus B. Other question? Okay, great. So here are a set of very important identities for set operations. You don't need to memorize that, but you just need to be aware of their existence. Sometimes you're going to use them to do some calculations. That'll be very useful. First, set operations satisfy the commutative law. It just means like if you just switch the order, it doesn't affect the results. A union with B is the same as B union with A. Okay. And also, A intersection with B is the same as B intersection with A. Okay. This can be easily seen from the one diagram, right? Okay, question. Is set difference satisfying the commutative law? No. Yeah, so just be careful. A minus B really is different from B minus A. Okay. Associative law. This is kind of similar to the arithmetic operations, right? So if you do a set of if you do sequential unions, it doesn't matter if you first do A union with B and then C, or you first do B union with C and A. Right? Similarly, intersection with A intersection with B and then intersection with C is the same as first do intersection between B and C and then intersection with A. This one is interesting, right? Distributive law, right? So if you kind of like combine union and intersection, then you cannot directly apply associative law, right? You have to apply the distributive law. So if you first union A and B, then intersect with C, it is equivalent to you first intersect A with C, and then B intersect C, and then union with them together. Right? To see this, again, we can always use Venn diagram to show this, right? This is A union with B, right? And suppose maybe I should. This is C, right? So what is A union B and then intersection with C? Yeah, from the graph, it will be this part, right? Just the overlapping part between C and A and B. Right? Does it make sense? You first do A and B union, that means you just cover all the blue circles, right? Combine all the blue circles, and then you intersect with C, will be just this part, right? Okay, so then if we look at, maybe I can draw it more clearly. So it will be yeah. So if we look at A intersection with C, right, from the diagram, right? I'm gonna use A intersection with C will be this part, right? Does it make sense? Right? So, right. And B intersection with C will be this part. Sorry, let me use a better color. You can see that. Then you just union them together. It form the whole A union B, the intersection with C, right? So you can simply verify this by the Venn diagram. Okay. Any questions so far? Okay. So then this De Morgan's law we just briefly mentioned in the last lecture, right? So if you this is about how do you couple the union with the complement or intersection with complement, right? So if we first do the union and then do the complement, it is equivalent to first do the complement, then do the intersection. I flip the union to intersection after doing the complement, right? Or if you first do the intersection, then do the complement, it is equivalent to first doing complement for A and B, and then do the union. Right? That's yeah. Again, we recommend you guys to draw some nice figures, better than me, to verify this. Okay. So once we have defined the sets, the sets and the events in the sample space, then we can talk about probability, right? Because after all, what we want is that okay, we want a systematic way to calculate the chance of all kinds of random events, right? So that makes us to define a function, which is called probability function, right? So the probability function will be defined on a sample space omega. And I use sample space omega, right? So for simplicity, right now, let's just talk about finite sample space, because if it's infinite sample space, there's a little bit rigorous issues. You have to redefine the domain of the function, must be sigma algebra. But for finite sample space, we don't need to worry about that, right? So if your sample space is finite, then every subset of the sample space will be some kind of event. And then the probability function will map this event to a number between 0 and 1. So this is called probability, right? So this function value represents the chance that event happens, right? That's called probability function. So again, whenever people are talking about probability, they're actually talking about a function, right? It maps some event to a probability number, right? So it's mapping between sets and numbers. And we require a probability function to be valid if first, the probability over the whole sample space is 1. That's easy to understand, right? Because whole sample space represents all possibilities, right? It represents, like, for example, if you roll a die, the whole sample space is 1, 2, 3, 4, 5, 6. It just represents, okay, you got point 1 or 2 or 3 or 4 or 5 or 6, right? No matter which choice, it must be that event. So the probability of the whole sample space is 1, right? And second, this is called separability. What does it mean? It means that if you got 2 events, right, A and B, and if they're not overlapping, meaning that the intersection between A and B is just an empty set, then the probability of the union of A and B should be the probability of A plus the probability of B. Does it make sense? Right? So intuitively, again, we can draw the Venn diagram, right? This is A, this is B, right? This is a whole sample space, which we denote by omega, right? So the probability, you can view it as some kind of area over this circles, right? So we just require that your area of this whole rectangle, which is sample space, is 1. Right? P of omega is 1, right? And we require that if A and B, these two sets, two events, are non-overlapping, then the probability of A union with B, which should be the area of both A and B, right, should be the area of A plus area of B, right? Right, because A and B are non-overlapping, right? The total area of A and B should be the summation of their respective areas. Right? Any question? However, if A and B are overlapping, meaning that their intersection is not empty, this really doesn't happen, right? This usually doesn't hold, right? Because if you look at the area of A union with B, it won't be the area of A plus area of B, right? You have to be subtracted by the overlapping part. Does it make sense? Right? Okay. So we want to use a simple example to showcase the probability functions, right? One is very common use example is called equal likely outcomes, right? So we define a probability function such that each element in the sample space has an equal chance, meaning that if you roll a die, every outcome has equal chance to appear, right? Then we can show that for any subset A, which represents some kind of event, right? This probability will be size of A divided by size of the sample space. For example, your omega is 1, 2, 3, 4, 5, 6, right? So if you look at the event, which is just a singleton set, right, which is 1, right? And the probability of this event is just 1 over 6, right? It represents equal likely outcome, right? Every outcome has the same chance to happen, to say. And if you look at another event, remember this event represents, natural language, it will be, you got point, no bigger than 3, right? Then this chance will be 1/2, right? Y is 3 over 6. The size of A is 3 here, and the size of the sample space is 6, reduced to 1 over 2. Right? Any question? Okay. So here we just do a little bit exercise, right, to reinforce our idea, right? So suppose you're picking a number out of a hat, right? And this hat contains a number through 1 to 100. Right? What are the following events and their probabilities? So first, what is the sample space? I heard that. Yes, exactly, right? It's kind of tedious to write, but to be clear, let me just write through it, right? So this is your sample space. You got 100 elements, right? So let us look at the first event, right? The number you pick it up, right, has a single digit. How do we represent that event? Any thought? Yes, exactly, right? Remember, even is represented by a set, right? So single digit, we only have a non-single digit, right? 1, 2, 1, 2, 9, right? And what's the probability? You see this even? Yes. The size of event is 9, right? The sample space is 100. That's it. How about this guy? The second event is you see a number that has 2 digits. What? Yes, 10 to 99, right? So, of course, it's a larger set, 10, 11, until you go 99, right? So what is the probability you see this event? What's the size of this event? 90, right? Yeah, you're gonna exclude the single digit, right? You're gonna exclude 100, right? So you got actually the size of this event is just 90, right? And then divided by the size of sample space, which is 90 over 100. Right? The number is multiple of 4. What's the event? Yes, exactly right. You just look at 4, 8, 4 multiply with something, right? It's 4, 8, 12, 16, blah, 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 until 100, because 100 can be divided by 4, right? So you will have like 25 such numbers. So the chance will be 25 over 100 is 1 over 4, right? So what's the probability that the number is not a multiple of 4? Why? Yes, exactly, right? So in this case, right, you don't need to really enumerate all possible numbers, right, in your set, right? You know that, okay, this event is just a complement of this event, right? We know that this event has probability 1 over 4, then its complement has probabilities 1 minus 1 over 4 is just 3 over 4, right? Okay, so please do some kind of exercise to get yourself familiarized with this kind of representation. So the last thing, I mean, it's a little bit stretch, but we want to talk about is called permutation, right? Why? Because later when we talk about repeated experiments, you see it's important to know the permutation, right? So the permutation is just an ordering of n tuple. N tuple means that you just place n elements together in some kind of list. Right? So if we look at a tuple 1, 2, 3, right? It has how many orders? How many orderings do they have? 6 orderings, right? You can put it 1, 2, 3. You can put it 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1, right? You just enumerate. You just permutate all possible orders. You're gonna have 6 orders, right? Okay. So in general, if you're talking about n tuple, meaning that your tuple contains n elements, then the number of unique orderings will be n factorial. Right? So this can be easily derived by saying, okay, in my first rank, it could be n choice, right? 1, 2, 3 until n, right? And then in the second position, because you know the first position, what is chosen, right? The remaining choice will be n minus 1. And you continue, you multiply all possible choices, it's just n times n minus 1 until 2. Any question? Okay. Yeah, I think it might be a little bit too dense to keep talking for 1.5. Let's just take a break for 5 minutes, and then we continue. Yeah, feel free to go to restroom or talk to your fellows, whatever, right? We'll continue in 5 minutes. Yeah.
我刚刚现在讲是跟那个之前学的210就是一样的，后面是不是不一样还是？
你说跟，sorry，你说跟之前什么一样？
就是有个课不叫 CS210，就有正的，这个咱们这个3130很像还是就后面不一样
220名字叫什么
？Discrete
？Discrete Math，Discrete Math 应该跟这个差别很大，因为你们要学什么图论之类的东西。
好像是。
对，图论这个应该，因为 Discrete Math 会讲 random variable。
就讲这个东西。
Oh, really? It's very different from my experience. 因为我们在上课的时候，
这 Discrete Math 好像是
应该不是 Discrete Mathematics 一般讲图，要讲数，要讲这个形式化语言、一阶位思维这些东西。但是它主要是偏重统计，因为我们要先从最基本的概念讲起，然后后面有一些这个 statistical inference，比如说我们要介绍什么 random variable，什么是 variance，怎么去估计它的无偏估计。然后如果你有无穷多的样本，最后你拿回去估计，那么它出来的就叫中心极限定理。
后面就不太有。
我个人my experience，因为I'm not teaching 2100，
因为我这学期还有一节数学课，也跟这个一样，最开始就好像是 foundation of analysis，最开始好像也是。
OK， 你说 foundation of data science 对吧
？foundation of analysis 就是 math 的课，不是？
那可能有一点不一样，但是那个地方那个课应该会更加 fundamental 一点，会让你算很多东西。我们这里边应该不会让你证明什么东西。Yeah, it's supposed to be in the course website. Yeah, is it? Oh, yeah, okay. Yeah, it's a course website. If you take a look at the in the Canvas app, if you look at syllabus section, there's a link to the course website, and you click into that is the course website.
Thank you.
Yeah. Okay. Yeah, let's continue. Yeah. Okay, let's continue with the probability function. So again, once you define a probability, right, which essentially maps all kinds of events to their probabilities, right? The probability essentially is a number, right, between 0 and 1, right? So we have some like intuitive properties about probabilities, right? So here we list a few, right? So the first one is called the inclusion-exclusion rule, right? So what does it mean? Like in general, if you got two events, A and B, remember A and B are essentially two sets, right? Then the probability of A union B is equal to probability of A plus probability of B, then subtracted by the probability of A intersection with B, right? This can be straightforwardly verified through the Venn diagram, right? So if you got A here, you got B here, remember the probability can be viewed as looking the area which those sets or operations of sets represent, right? So if you look at area of A union with B, it can be represented as the area of A covers, right? And then the area of B covers. But then you find a problem. You find that the overlapping part actually is counted twice, right? That's why you're going to subtract by the area of the overlapping part. That's how we get this inclusion-exclusion rule. Right? But now I got a question. What if A and B are non-overlapping? Then what does this guy mean? Empty, right? So that means this guy is empty, and it's empty, the probability over an empty set, which called empty event or null event, is 0. Does it make sense? Right. Okay, so complement rule. The probability of A complement is 1 minus the probability of A. Again, this is very intuitive if we draw the Venn diagram, right? So this is the whole sample space. And we know that the probability over the whole sample space is 1, meaning that, okay, this the area of this whole rectangle is 1, right? And now, this is your A. And the probability of A complement is just the area of omega excluding A, right? That's why it's just 1 subtracted by the area of A, because the total area is 1, right? Okay, difference rule. If you look at the probability of A minus B, remember this is also an event, right? So it is a probability of A subtracted by probability of A intersection with B. Why is this, right? Again, let's check, right? This is A. This is B, right? This is a whole sample space, right? So A minus B, again, is just A excluding all elements in B, right? So that will be just this part, right? So your probability of A minus B are the area of this part, which I draw with the red line, right? So with this one, the area of this part is actually, you first get the whole area of A, right? Which is green shape, right? Subtracted by the area of the overlapping part between A and B, right? Overlapping area of A and B. Then you get the red part. Does it make sense? Right? Again, I mean, if you feel uncomfortable, just after class, I try to draw it. You'll see this, right? It's really straightforward. Okay, exercise. Try deriving these rules from the definition of a probability function and draw a Venn diagram to convince yourself they work, right? This is really helpful for you to understand the probability function and their relationships. Okay, so now let us introduce the concept called conditional probability. Why do we introduce conditional probability? Because we want to look at the relationship between different events. Right? One possible scenario will be, okay, if some event happens, then what is the chance another event happens, right? So like, general, my chance to getting up late will be low, right? Say just 20% chance, right? 0.1, 0.2. But given there's a big snow in the morning, then what's the chance that I get up late in the morning? It will increase a lot, right? Probably will be 80% chance, right? So that's the difference. You see that, right? So once you condition on some other events, then your event of interest happens will likely change a lot, right? So here is the formal definition. So we denote the probability of event A given the event B happen as P A given B. And how do we calculate this? How do you quantify this conditional probability? It is just divide the probability of A intersection with B by the probability of B, right? So again, we want to visualize it using Venn diagram, right? So this is your sample space, right? So this is A. So this is B, right? So P A given B is conditional probability. What does it mean, right? It means that I'm gonna calculate the area of A intersection with B. So this area is P A intersection with B, right? But that's not N. It's just the denominator. Then we're gonna divide this, area, or we'll calculate the ratio between this overlapping area with the area of OB. Right? That is the conditional probability. Does it make sense? Right? So you see that usually it will be bigger than just calculate the denominator, right? Intersection with B, because you're dividing some number be less than 1, right? You're actually amplifying. Any questions so far? Okay. So this is definition, right? But in practice, people is more in favor of writing in this way, writing the probability of the intersection between A and B as a decomposition, decomposed as the probability of B, right, times the conditional probability of A given B, right? So the probability of a single event is usually called the marginal probability. Why? Because just talking about a single event, right? And this one is called conditional probability. Okay, so now let us use this decomposition to do some kind of practice using some concrete example, right? So here is our random experiment, right? You're given 2 boxes. You have total 5 balls, right? 1, 2, 3, 4, 5, right? And the first box contains balls 1, 3, 5, and the other contains balls 2 and 4, right? So you're gonna first randomly pick a box. Then, given that box, you're gonna randomly pick a ball. You see, actually, our random experiments contains 2 steps, right? First, you kind of random pick a box. Then, given the box you picked, you're gonna random pick up the ball inside the box. So then we want to calculate what's the probability you're gonna pick up the ball to, right? So this one can be represented. We can introduce 2 events, right? The first event, A, is you pick a box, right? Of course, A could be 1 or 2. Box 1 or box 2, right? B is about you pick a particular ball, and B could be 1, 2, 3 until 5, right? So here we talk about the probability of picking a 2. So it could be the events is that A is box 1. B is ball 2. And A is box 2. B is ball 2, right? Because eventually our event will be just pick the ball 2, right? So it will be decomposed as 2 events. One is that, okay, you pick up box 1, then you pick the ball 2. Or you pick box 2, then from box 2, you pick ball 2, right? Right? So and for the first event, A is box 1 and B is ball 2. This is actually an empty event, right? Why? Because box 1 contains 1, 3, 5, right? It doesn't contain ball 2. Right? So that basically means this event is just empty. Does it make sense? Right? And the only possibility is that, okay, you pick box 2, then from box 2, you pick ball 2. Right? Does it make sense? Right? So that means the probability of picking 2 is just the probability of A is box 2 and B is ball 2, right? Does it make sense? Right? And then using our decomposition, right? So we know that this guy can be written as first the marginal probability that you pick box 2, and then the conditional probability you pick ball 2. Given A is box 2, right? So the marginal probability for the first event, A is box 2. What's that? 1/2, right? Because you randomly pick up a box, right? Right? It's just 1/2. And how about the conditional probability? Given box 2, you pick the ball 2. Also 1/2, right? Why? Because you only have 2 balls in box 2, right? You pick up 2, you got half, right? So multiply them together, you got your probabilities 1/4, right? Any question? Right, this is a little bit, I mean, abstractive, but here we want to introduce a much more intuitive way to represent this, right? So actually, we can draw a tree diagram to show all possible events, and you see their joint probability is decomposed step by step, right? So in the first step, we pick a box, right? And pick box 1, you got probability 1/2. Pick box 2, you got probability 1/2, right? And given box 1, right? This is condition, right? Conditional, you have already picked box 1. Then you got equal chance to pick any ball in the box, right? For the box 1, you have 3 balls. So you got 1/3 probability to pick ball 1. You got 1/3 probability to pick ball 3. You got 1/3 probability to pick ball 5, right? And remember, box 1 just contains 1, 3, 5, right? And if you look at the box 2, right? Conditional, you pick box 2. You're gonna only either pick ball 2 or ball 4, right? So you have the conditional probability to pick ball 2, given you pick box 2, will be 1/2, right? And the conditional probability to pick ball 4, given you pick box 2, is 1/2. Does it make sense? Right? And then if you want to look at what's the probability of picking each ball, what you need to do is just multiply the marginal probability and conditional probability along our paths. Right? So the probability you pick ball 1 is your probability you pick box 1 multiplying the conditional probability you pick ball 1 given box 1, right? Which is 1/2 times 1/3 is 1/6. Right? The probability you pick, you pick ball 3 is first the probability you pick box 1. Then given box 1, you pick ball 3. So it's 1/2 times 1/3 is 1/6, right? Just keep doing this, right? And similarly, your probability you pick ball 2 is decomposed. First, your probability of picking box 2, right? then given the conditional probability that given you pick box 2, you pick box 2, 1/2, multiply them together, 1/4. Right? Any question? Okay, great. So, in statistical inference and experiments, what do you often say? There's two terms, right? Sampling with replacement, sampling without replacement. What does it mean, right? What does it mean for sampling with replacement? It's like you're doing those experiments totally independent to each other, right? So here is the example, right? I have a box. The box contains 10 red and 10 green balls, right? And of course, I'm gonna have like equal chance to pick up any ball from out of this box, right? I draw 2 balls with replacement. What does it mean? It means I'm gonna randomly pick a ball from this box and take a look at this color. Then I put the ball back to the box. And then I do this again. Right? This is called sampling with replacement. Right? So now if you want to ask, what is the probability you pick up 2 red balls? It's like, okay, first, your probability in the first experiment, right? The chance you pick the red ball is what? 1/2, right? 10 over 20. And remember, when you do the second experiment, you have already put the red ball back to the box, right? So your second experiment is totally independent of the first experiment. It's still like, okay, given these 20 balls altogether, I pick up a red ball. So the second, given you pick up red ball, and then you pick another red ball, it's still 1/2, right? So just multiply them together, the chance is 1/4, 0.25. Sounds right, right? Okay. So sampling without replacement, it means that the experiments are related to each other. The previous experiment can alter the second experiment. Right? So again, I have a box with 10 red and 10 green balls. I draw 2 balls without replacement. What does it mean, right? It means that in the first experiment, when I draw a ball, when I look at the color, I'm gonna throw out the ball. The ball will never come back to the box. So that means when I do the second experiment, the number of balls is reduced by 1. It's no longer 20. Right? So take this example again, right? I want to look at what's the probability of picking up 2 red balls. It just means, okay, in the first experiment, I pick up a red ball, right? So this probability is still 10 over 20, half. But then when I do the second experiment, I have threw out that red balls out of the box. So in the box, the remaining balls will only have 19 balls, right? I have 20 balls in total. I pick up red ball, I throw it away. So then the box only contains 90 balls. 9 of them are red and 10 are green. Why 9 of them are red? Yeah, we haven't picked up a red ball in the first experiment. I throw it away, right? So that there will be only 9 red balls remaining. Then the probability you pick up a second red ball will be 9 over 19, right? And then you multiply them together, you see that it will be slightly less than 0.25. Okay, so this is called sampling without replacement. So there's difference. Any questions so far? Okay. So, I guess it's not. Okay, I think we can work out this problem in the beginning of the next lecture to kind of like reinforce the concept we have learned. Okay, see you on Thursday.